This example is integrating a cone, so it's z equals square root of x squared plus y squared, and it's, so this cone right here, and then it's over this circle, and the circle has radius 1/2, so it goes from 0 to 1 here on the x-axis, and then it's centered at x is 1/2 and y is equal to 0. Alright, so this looks like a nice case for polar, but the first thing is, unless you remember the equation of this in polar, you have to derive it. So the first thing to do is actually to figure out what this is in Cartesian. So you can use that. So the equation of a circle in xy coordinates, it's the radius squared. So the radius of the circle is 1/2. So it's going to be 1/2 squared is equal to, so we're going to have x, and it has to be shifted, so it's x minus 1/2 squared, then plus y squared. All right, so the typical form is the radius squared equals x squared plus y squared, but we had to add in this shift because the circle isn't centered at the origin. Right, now from here, we're just going to do the polar substitution. So, right, we have x equals r cosine of theta, and we have y is equal to r sine theta. So plugging those directly in, so let's simplify as we go. So 1/2 squared, that's a quarter, equals, and here we have r cosine of theta minus 1/2, still squared, plus, then y is r sine, so square that, you get r squared sine squared of theta. Right, so that's not in a very nice format. We'd like to get r equals something. So let's go ahead and see if things get better if we expand this piece out. So we have 1/4 equals, so FOIL, first, outer, inner, last, we get r squared times cosine squared of theta. In the middle, we have r cosine theta times negative 1/2, and then there's two of them, times 2, so we get a total of minus, the 2 and the 1/2 cancel, so it's just minus r cosine theta. And then we have the negative 1/2 times negative 1/2, so positive 1/4. And then we still have the r squared sine theta on the end. Sine squared theta. All right. All right, well, one thing we can do is we can cancel out the 2/4, and we can also combine the r squared cosine. So here, right, I'm going to have 0 is equal to, I have r squared, then I have cosine squared of theta plus sine squared of theta, right? And then I have my minus r cosine of theta. But then cosine squared plus sine squared is 1, so we have 0 is equal to r squared minus r cosine of theta. And then here we can actually factor out an r. So we get r times r minus cosine theta. So now if we want to actually solve this, we have 0 equals r times r minus cosine theta. Well, one option is r equals 0, but that definitely doesn't represent this entire circle. But the other option, so r equals 0, or r is equal to cosine theta. And it turns out, yes, cosine theta does represent that entire circle offset on the axis. So that's what we can use inside the polar integrals, the upper and lower bounds. And then this one you do have to be careful. So right, going back to polar, you do have to know that in order to trace this out, and this was in the previous videos as well on the webpage, is we want to make sure that we pick r of theta is equal to cosine theta. And to trace out that circle and to make sure r is never negative, we want theta between negative pi over 2 and pi over 2. So that'll give us our integral bounds. So we're going to have integral, so let's go ahead and write this out. So let's start with got my region R, this is going to be in xy coordinates. So before we were integrating, z equals square root of x squared plus y squared, so we still need to do that. We're going to have to do our change of coordinates here. So we've got x squared plus y squared and dx dy. We want to translate that into polar. So for polar, we do know the bounds on the polar now. So it's going to be theta is negative pi over 2 to positive pi over 2. And then the r bounds, right, in this circle, we're always going from r0 to the edge of the circle there. And that circle has equation cosine theta, so it's going to be r equals from 0 to cosine theta. All right. On the interior, though, we have square root of x squared plus y squared. Well, kind of same thing over here. If we have x is our cosine theta, y is our sine theta, we plug that into here. X squared plus y squared is r squared. So it ends up being the square root of r squared. And then we also have the change of variables here. So dx dy turns into r dr d theta. All right, and if you simplify that, integral, so negative pi over 2 to pi over 2, integral 0 to cosine of theta, I think I'll have just enough room, square root of r squared, it's actually absolute value of r, so, but because r is always positive, we can leave that alone. So we have square root of r squared is going to be r, then r times r from the r dr d theta gets us r squared as the integrand, and then we still have our dr d theta over here. All right, so now that we've set up the integral, I'm going to go ahead and go to a new sheet so we can actually perform the integration. Now to evaluate this integral, so right, we have our r squared, so we have to integrate that. That ends up being, let's do quite a lot here, so negative pi over 2 still to pi over 2. We haven't done anything with the theta integral yet. But the integral of r cubed is going to be 1/3. Sorry, the integral of r squared is 1/3 r cubed. We're going to evaluate that from its bounds, from 0 to cosine of theta. And then we still have our d theta on the end here. All right, well, if we plug in cosine of theta, we're going to get 1/3 times cosine cubed theta. Then we're going to subtract. If you plug in 0, we get 1/3 minus 0 cubed. So it ends up just being, we still have our integral bounds about here, pi over 2. So it's 1/3 times cosine cubed of theta, d theta. Right now that's a little bit annoying, but we can use a trig identity for that. So I'm going to split this, so I'll do a little bit of work over here, I suppose. So cosine cubed of theta, we're going to split that into cosine theta times cosine squared of theta. Then we can split that into cosine theta times 1 minus sine squared of theta. All right, and that ends up equaling cosine of theta, which looks like we can integrate it, minus cosine of theta times sine squared of theta. And we can't actually integrate both of those. So this one we end up, it's a sine cubed, and the chain rule will pop out the cosine. So rewriting that back over here, we have integral negative pi over 2 to pi over 2, 1/3, and I'm actually going to take the 1/3 out front, so let me go ahead and squeeze that in. And we have cosine of theta minus cosine theta sine squared of theta, d theta. Well, that ends up equaling, so integral of cosine is positive sine, and let me not forget the 1/3. 1/3, use square brackets here, so integral of cosine is sine of theta, and we're going to have a minus 1/3 sine cubed of theta. Right, the way that works out, right, you take the derivative of sine cubed, it's going to pop out a 3, cancel out the 1/3 fraction, and then sine cubed turns into sine squared, but then from the chain rule, you also have to pop out an integral of sine, sorry, a derivative of sine, which gave us the cosine from before. So that all works out, and we have to evaluate this from negative pi over 2 to pi over 2. All right, so going back to sine, let me just go back to here. All right, if we do sine, it looks like that. And so that point is pi over 2, and this point is negative pi over 2. So they end up being positive and negative 1. So I have my equals, I have my 1/3 still. All right, so we have sine of pi over 2, which is 1. So I've got sine of pi over 2, 1, minus 1/3. Sine cubed of pi over 2, but again, sine of pi over 2 is 1, so we have 1/3 times 1 to the third. Go ahead and put that in. Then minus for the other integral bound. All right. So now we have negative pi over 2 plugged in. So sine of negative pi over 2 is -1. All right. And then we have our minus 1/3 times -1 cubed. Let me see if I get the right number of parentheses there. Okay, so then simplifying that. All right. So we have 1/3 minus 1/3. So let's see, 1/3. 1/3 minus 1/3. Well, that's 2/3. Then we have a minus. Okay, -1. All right, so -1. -1 cubed is -1. Negative times negative positive. So in here we have -1 plus 1/3. Then it's a minus as well. So that would be -2/3. So it's, I think I got this, it's 2/3 plus 2/3. So the first bit here simplified to positive 2/3. And then including the minus here, this next bit also simplified to positive 2/3. Well, that's 1/3 times 4/3, which is 4/9. So there you have it. You need trig identities typically to do polar integrals, but at the end you can finally get your answer.